Alright, so we have a wonderful problem here that I think is just a good source for deep mathematical conversation around patterns and rates of change. So we're going to go through it, and I know if you just, this is not even the whole problem here, and it might seem really tedious. Oh, it's one of those long word problems, I don't want to deal with it. Hang in there, because this problem has a lot of wonderful aspects to it. So let's start by reading the premise of the problem, and then we'll go through it piece by piece. But the premise is that in many athletic competitions, medals are awarded to top athletes, right? So think of the medal podiums that athletes stand on, because here they say the medals are often awarded in ceremonies with medal winners standing on special platforms, right? Of course, they're referring here, the platforms, to those podiums that the athletes stand on. The sketches show how to make platforms by stacking boxes. So here, right, let's say we have one podium for the person to stand on. Here we have two podiums to stand on, but one is higher for the other, right? The winner would stand on the higher stack of boxes. And then here we have first, second, and third place, right? The first place person would stand on the highest stack, second person on the second highest stack, and the third person stand on the third highest stack. What they're kind of describing for us is that if there's one medalist, you need only one box for them to stand on. And with this design, if there are two medalists, that wouldn't require two boxes. It would require 1, 2, 3 boxes for the medalist to stand on. And if there are 3 medalists, it would require 1, 2, 3, 4, 5, 6 boxes for the medalist to stand on. So already you can see that the shape is growing each time, and there's certainly a visual pattern here to be seen. Every time we have a new medalist, we have another row being added that's higher than the previous ones. So they would just want us to kind of use that to fill in this table right here. Now the table, if you look at the independent variable, that's the number of medalists. We'll set that as x. And then the number of boxes needed is based on the number of medalists. So we know, and this is exactly what they show us up here, if there's one medalist, you need one box. If there's two medalists, you need two boxes. If there are 3 medalists, you need 3. And what would you need for 4 medalists? Well, if we don't see a pattern in the table, I would just suggest that you draw it out. Here, what you can do is just do a quick sketch here, right? The first lowest row of boxes, we can set that up. Okay, so you've got now 4 medalists. 1, 2, 3, 4. The last place person will stand on the lowest stack. Then I won't write 1, 2, 3, 4. That'll confuse us. But the lowest stack is right there. Then we add 1 box here, 2 boxes here, right, and 3 boxes there. Okay, so this is what it would look like. And now how many boxes do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes altogether. So we can fill that in our table. So it goes 1, 3, 6, 10. And we can keep doing this, but you can imagine how tedious that might become. So let's look at a pattern here. When we are going up by medalist, we are going up by 1 each time. So that's nice. We're always going up by 1 there, so we can track kind of the rate of change. If we're going up by 1 each time, here we go up by 2. That's our rate of change there. But then we go up by 1 in number of medalists. We don't go up by 2 again, we go up by 3. So the rate of change has changed. It's increased by 1. So first the number of boxes went up by 2, then it went up by 3, and now it's going to go up by 4. So you see that the rate of change, the amount of boxes we need, is growing each time by 1 more. So next we won't need 4, we'll need 5 more to get 15. And then we'll need 6 more to get 21, 7 more to get 28, and 8 more to get 36. So now we have those values, and they want us to make a graph based on these values. Alright, so if we set this up, right, our graph, we have our independent and dependent variables. So the independent, again, that's just going to be the number of medalists, and then the number of boxes will be the dependent variable. Okay, so we set this up, and here I'll write that in. So our medalists here, right? And we don't need this here anymore. I'll clear this off. Oops, wrong tool. I need the select tool to clear that off. Okay, clear that off. And now here on the y-axis, it's not medalist, of course, but the number of boxes needed. Number of boxes. Okay. So really, if you think about what we just did, if we set the number of medalists to the x and the number of boxes to the y, we could think of them as points x, y, where the top row here will represent your x values of your points, right? And the bottom row will represent the y value of your points. And so we just plot those points. First we have this point right here, 1, 1. So we can set that up, right? 1, 1 would be here, let's say. Right? That's 1, 1. And then I'm definitely estimating here in the graph. We have 2, but it goes up to 3 here. Okay? And then we have 3, and it goes up to 6. So it's double that height. Okay? And then it goes up to 4, right? But then it goes to 10. So maybe right here. And then 5 goes up to 15. Right? And you can see that if we kept doing this, and we could keep doing it, I guess maybe I'll just drag this down a little bit. Of course, if you're trying to be accurate here, which you should, I hope, you would want to use graph paper for this. Set this up. So we're going to kind of extend these a little bit here so we can see how this looks. Right. It should help us a little bit, although I don't think it'll even fit because you see the rate of change is going so fast. But okay, so we have 1, 2, 3, 4, 5. Now we need 6 at 21. Okay, so 6 will be all up here at 21, let's say. And 7, 28, and we're running out of room again. So 7 and 8 would be all the way up here at 36. So these are our points. And what you realize is that this is not linear because if you attempt to draw a line through any two of these points, let's say these 2 points right here, what happens is you can imagine this line does not cross any others. So not all the points lie on a line, right? That wouldn't work, and you could try the combinations. Let's say you tried, okay, let me try these 2 points here. It's a very fast rate of change, but notice the line will not cross the other lines. Since there's no one line that goes through all of them, this is not a linear relationship, and that means, of course, that the rate of change is not the same. And in fact, if you were to try, right, 0 would be 0, but you can kind of graph this out. Here we kind of have a nice curve, right? So this has an exponential or quadratic relationship, which we'll explore a little bit in the next video when we create an equation for this. But here you can see it's not linear, right? That's the key. Because the rate of change, even in the table, was increasing every time, that means the rate of change is always changing. It's not linear, it's not constant. So here when you describe the pattern, that's one thing you want to refer to, is how the rate of change is always increasing as you go along, and that no line can go through any 2 points. It's not linear. So now that's one way of looking at the metal platform, and here in part D they kind of changed the question around, looking at the same concept though, and that's part of the richness of this question, is that now we're going to observe a pattern not with the number of boxes but the amount of carpet it will take to cover the boxes, and that changes everything. Right? So here, again, we're looking at these boxes, except now we're told that they're 1 feet, right, high and 2 feet wide. And a red carpet starts 10 feet from the base of the platform. So that means that this distance right here, right, is 10 feet. So the carpet has to cover 10 feet plus these platforms right here, and it ends there. It doesn't come down on the far side over there, but it goes right up to the top. So we want to know for any number of steps, how much carpet will you need? Well, if we just had the one step right here, it would be 10 plus 1 plus 2, right? So it would be 13. Okay. If we have 2, it would be 10 plus 1 plus 2, and then what would you add to it? Well, you'd add another 1 and another 2. Right? Because we don't need to deal with the far side over there. So we add another 1 and another 2. That's 3 altogether, so that would be 16. And then with 3 platforms, we'd add another 1 and another 2 on top of what we added before. So another 3 in total. So every time a new column is added, we need how many more? Well, so far it's 3 for each, right? And that's because you're only adding really the height and width of each new box. So it's going to go up by 3 each time. You can test it, but then we get 22, 25, and 28, and 31, and 34. So now you notice the rate of change even before we graph it, and they do want us to graph it, but before we even do that, every time we went up by one platform, our rate of change was to increase by 3. So that's important, right? Our rate of change, our slope, is always going to be 3. So I would make a note for myself that m, which we usually use for rate of change or slope, is going to equal 3, right? In other words, if carpet length is the y variable, because that's the dependent variable, excuse me, and the number of steps is the independent variable, that means the rate of change is 3 more feet of carpet for every 1 step added. So when we say 3 as the slope, that really means that the delta y, or the change in y, in this case the change in carpet length, over the delta x, or the change in number of steps, is 3 more feet of carpet for every 1 step. That's the ratio, which of course is just 3, but that's a little bit of the idea behind it. And this is constant or linear, right? Because it's always going to be 3 more feet for every 1 step, and that'll form a straight line for us. So now let's set this graph up. I'll do a little bit better of a job here. I'm just trying to be aware that our highest value is 34 and our lowest value is 13. So let's set this graph up. We only need to go 1 through 8 on the x-axis. So I'm going to, first of all, I'm going to move this little note. We don't need this here. It's going to block our graph. Move it down here. And then maybe, I think if I draw a nice long vertical line, right, that should be enough to cover this graph. Okay, so now the x-axis is what? Well, now it's the number of steps. Before, the number of steps was the independent variable, and now it's the dependent. Before, the number of steps was the dependent variable, and now it's the independent variable, right? See, that's changed quite nice. Number of steps, and then the y-axis is going to be equal to carpet length. And I could have labeled the axes like I did before, I just don't have the room here on the page. Okay, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8. So here we go, 0, I'm going to go up maybe by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, right? 22, 24, 26, 28, 30. Okay, still a rough graph, but it'll work. 32 and 34. So now, again, we have our x and our y's. These are our points. What's our first point then? Well, that's 1, 13. Right, so 1 and 13. And then 2 and 16. Right? So 13, here's 10, 12, 14. So, sorry about that, the 13 should be a little below it. And then 16, so 12, 14, 16 is right here. Okay. And then 3, 19, right here. 4, 22, right here. Right, that lines up. There's the 4. Well, it doesn't line up very well. Sorry. Let me fix this. I shouldn't be sloppy like this. Okay, 3, 19. 4, 22. And 5, 25. 22, 24. So 5, 25, about here. And so forth, right? But the point is, and I guess I'll finish it, 6, 28. Right here. And 7, 31. Sorry, I have to finish this. And 8, 34. Still not perfect. But the point is that if you line these up, and they come down here to 10, they do all fit on one straight line, right? Of course, they don't for me because my drawing is slightly off. But you should notice a few things about the graph here is that all the points fit in a straight line as a constant rate of change. That it crosses the y-axis here at the y-intercept. Remember, intercept, that means cross or meet. So it meets the y-axis at 10. And that makes sense because regardless of the amount of boxes, we do need 10 feet of carpet. So even when the amount of boxes is 0, when x is 0, your carpet is 10. And usually the y-intercept you'd only say 10, but I'm listing it as a point. And the slope is 3, and that means that pick any point, and that means to get from one point to the next, right? The rate of change is, well, 3 to 1. 3 more feet of carpet for 1 more box. And you can expand that. If you went up 2 points, what would happen? Well, you would go 6 and then over 2. But going up 6 and over 2 is the same ratio as going up 3 and over 1, right? 3 to 1 does equal 6 to 2. So that's the fun part. You can pick any 2 points, and that slope will be constant. So when you describe this pattern, you want to refer to the intercept, and that's they ask us to do here in F. Describe the pattern, describe the rate of change as being constant, and name it as a number or equation so that you understand that this is a linear relationship. Now in the next video, we're going to build off of this with some equations. We're going to actually deduce what these functions really are that predict any number of carpet for any number of steps and any number of platforms for any number of medalists. It's a really nice expansion to the problem. All right, thanks.